Laurel Wilt sort of exemplifies one of the problems that we're dealing with when it comes to natural resources in the United States. It's introduced exotic species that threaten both agriculture and natural forests. And one example of this is the red bay ambrosia beetle. They're tiny. They're about the size of Lincoln's nose on a penny, if you can imagine how big that is. This little beetle feeds on fungi, and it looks like a white mold essentially. But this fungus is carried in specialized structures inside the mouth part of the beetle. And the beetle bores into the tree, making very small holes, like you can see here. And inside of the tree, it makes little galleries where it cultivates its fungus, its symbiont. And the eggs hatch and the larvae feed on the fungus, and they leave the tree carrying the fungus with them. Well, that fungus, when they introduce it into the tree, is capable of moving in the vascular tissue and the water conducting tissue of the tree, and it causes the tree to basically wilt and die very quickly. And so this is what we know as laurel wilt. And so we're trying to better understand the mechanisms by which this is happening and figure out how we can maybe manage this and keep this from causing all the impacts that it's causing to our native forests. There's a lot of different approaches that we can take, and we're sort of looking at it from a holistic, whole system approach that involves a lot of different collaborators.
You need a combination of people that each understand the components and also the whole. And so then we have a plant pathologist. And then we have people who study tree physiology and who study the interactions between the fungus and the tree and the beetle. And we have entomologists who specialize on where the beetle came from, how it's related to others. Are others going to do the same? But you also have entomologists that study the behavior of the beetle, that study how it's sniffing around and smelling the trees and deciding which tree to attack and which trees to just pass. Lots of people are needed to even understand how it works.
One of the things I'm excited about now is we're starting to understand some of the mechanisms in the avocado plant, the avocado tree, that are responsible for it resisting this disease. And my hope is that very soon we're going to be able to come up with ways of managing the different varieties of avocado and use that information then to manage the disease successfully.
One of the things that we've done is we've gone out and looked for survivor trees where most of the trees have died off. 95 to 99% of the red bays have died within 3 to 4 years. And we look for those rare surviving trees, those individuals that are still alive after the disease has basically wiped out everything else. And then we have vegetatively propagated those trees by taking cuttings and then growing new trees from those cuttings. And now we're testing to see if those have resistance to the disease. And as it turns out, some of them are in fact resistant. And so we have hope that we'll be able to use those resistant trees for restoration projects, to be able to maintain the trees for butterflies and other natural resources that we'd like to preserve.
The more we learn about this disease, the more difficult we realize it's going to become to manage it. We've made significant progress. We understand so much more about the disease now than we did before. We have a lot more to learn. There is a lot of exciting research going on.
We have such a great team of collaborators and such supportive staff to work with. It's really a fantastic place to work. Being an IFAS is really good because we have so much support. We have stakeholders that are out there basically arguing for the importance of IFAS and for what we do. And I think it's really easy for the general public to see that IFAS is directly involved in solving problems that will help if they're solved, will help make the state of Florida a better place to live.